All right, let's start with the easiest case first. That's when the auxiliary equation has real and distinct roots. So again, we're working with a homogeneous linear differential equation. Homogeneous means 0 on the right-hand side. And this linear differential equation with constant coefficients has y and its derivatives on the left-hand side, a linear combination of y and its derivatives. So to solve this, we're expecting solutions of the form y equals e to the rx. What are? Well, we form this auxiliary equation from the differential equation, turning every kth derivative of y into a kth power of r. So pretty much just copying down with the coefficients, and every derivative turns into a power of r. So if the roots of the auxiliary equation are real and distinct, let's say R1, R2 up to Rn, then e to the R1x, e to the R2x, etc., e to the Rnx, oops, that x goes in the exponent, is a basis of the solution space. So you just take those roots and put them in the exponents. That's all there is to it. So for example, let's find all solutions of the homogeneous equation y double prime plus 3y prime plus 2y equals 0. So we'll solve r squared plus 3r plus 2. I should mention that y is the 0th derivative of y. So it turns into r to the 0th. It just disappears. So we'll solve this equals 0. And I think this factors. This factors as r plus 1 times r plus 2. The solutions, or the roots, are r equals -1 and r equals -2. So all solutions have the form some multiple of e to the -x plus some multiple of e to the -2x. And that's all there is to finding all the solutions. Now, another question we could ask is, of this infinite family of solutions, this two-dimensional vector space, which solution satisfies certain properties? So which solution satisfies, say, y of 0 equals 3, y prime of 0 equals -1. So that those two pieces of information might help us solve for C1 and C2 to get one solution in this solution space that has those properties. Well, y of 0 equals 3 means that, well, if y is this, and we plug in x equals 0, and we have C1 e to the 0th is just 1, plus C2 e to the 0th is just 1, plus C2 equals 3. All right, so that tells us that if our solution satisfies these properties, the coefficients C1 and C2 add up to 3. Of course, that's not enough to figure out what C1 and C2 are because there are infinitely many solutions of that equation. But knowing that the derivative is -1 means that, what's the derivative of this? Negative C1 e to the negative x negative C1 e to the 0 for plugging in 0, minus 2C2 e to the 0 equals -1. Or in other words, I guess I could have just left off the e to the zeros because they're 1. Minus C minus 2C minus C1 minus 2C2 equals -1. All right, now we've got 2 equations and 2 unknowns, so we can solve these. In fact, if we let the second equation be second equation plus the first, then we get 0C1 minus C2, minus 2C2 plus 1C2 is minus 1C2 equals 2, which means that C2 equals -2. And if C2 equals -2, then I guess C1 equals 5. So the solution satisfying y of 0 equals 3, y prime of 0 equals -1, is y equals C1 is 5 e to the negative x, C2 is -2, minus 2e to the -2x. So it's a typical question. What is the family of all solutions and which solution satisfies certain properties? Let's do another example. Let's find all solutions of y double prime plus 3y prime plus y equals 0. So I just changed the 2 to a 1 here. Well, this is going to make the solutions a lot different. So we'll solve r squared plus 3r plus 1 equals 0. And I can't think of two factors of 1 that add up to 3, so we'll have to use the quadratic formula. So r is one of the numbers -b plus or minus square root of b squared, 9, minus 4ac, minus 4, all over 2a, all over 2. So that's -3/2 plus or minus square root of 5 over 2. So all solutions have the form y equals something e to the -3/2 plus -3 plus root 5 over 2. Plus some other constant e to the -3 minus root 5 over 2. And we could ask the same type of question. Which one of these infinitely many solutions satisfies certain properties? Often the properties are y of 0 equals something, y prime of 0 equals something. So let's say y of 0 equals 1, y prime of 0 equals 2. So if y of 0 equals 1, that implies that, oops, this should be an x here. That constant times x and that constant times x. So if x is 0, then this is just c1. If x is 0, that's just c2. And that equals 1. Y prime of 0 equals 2 implies that, let's see, y prime of 0 is we've got negative 3 plus root 5 over 2 c1. Y prime of 0, so we'll have e to the something times 0, which is e to the 0, which is just 1, plus negative 3 minus root 5 over 2 c2 e to the 0, which is 1. So that equals 2. So now I guess we'll have to do row operations. Let's see, row 2 becomes row 2 plus 3 minus root 5 over 2 times 1. Because if we do, if we do that, then the minus 3 and 3 will cancel, the root 5 and minus root 5 will cancel. So now we get, so we'll have 0 c1, and we'll have 1 times this plus that. So 3 minus root 5 over 2 plus minus 3 minus root 5 over 2 c2 equals 1 times this, 3 minus root 5 over 2 plus 2. So what happens over here? 3/2 and minus 3/2 cancel each other out. Minus root 5 over 2 minus root 5 over 2 is minus root 5. So all that's left is minus root 5 c2 equals 2 is 4/2. So we've got 7 minus root 5 over 2. So that means that c2 equals, if we multiply both sides by let's say negative 1 first, then we've got root 5 minus 7 in the numerator divided by 2 root 5. And maybe I'd like to get the root 5 out of the denominator. So if I multiply top and bottom by root 5, then I got 5 minus 7 root 5 all over 10. Maybe that's slightly nicer. Alright, that's what c2 is. c1 plus c2 equals 1. So that means that c1 equals 1 minus that, which is 10/10 minus that, minus 5 minus 7 root 5 over 10, which is 10 minus 5 is 5. 5 plus 7 root 5 over 10. So the solution we want is the solution satisfying y of 0 equals 1, y prime of 0 equals 2 is y equals c1, we said was 5 plus 7 root 5 over 10 e to the first exponent is negative 3 plus root 5 over 2. X. And then the second coefficient C2 is 5 minus 7 root 5 over 10. e to the negative 3 minus root 5 over 2x. Now, not all polynomials factor as x minus an integer times x minus an integer, so we have to be ready to deal with square roots sometimes. The end.